600 million kilometers from where you are sitting, a moon is glowing at both ends. Not the whole surface, just two belts of light, one wrapped around its north pole, one around its south. They are auroras, the same kind of light you would see over Alaska or northern Norway, and they are rocking back and forth, side to side, like a slow metronome, over and over, because the moon they belong to is being dragged through the magnetic field of the largest planet in the solar system. Astronomers watched those belts of light for 7 hours, using the Hubble Space Telescope. They expected them to swing about 6 degrees. Instead, the belts barely moved. They rocked 2 degrees. 2 degrees is roughly the width of your thumb, held out at arm's length. That is the entire measurement. That is the whole discovery. Because something inside that moon was pushing back. And nobody expected Ganymede, a frozen, cratered, dead-looking ball of rock and ice, to be doing anything like this. Stick around, because I am about to walk you through what scientists actually confirmed about the ocean inside Ganymede, how they proved it without ever landing on it, and what is going to happen there in 2034. And hit subscribe now, because this channel breaks down real space discoveries, without the exaggeration. Let's go back to where this story actually begins. In January of 1610, a 45-year-old mathematics lecturer in Padua was doing one of the most tedious jobs imaginable. Night after night, in the cold, he pointed a homemade tube of glass and lead at the same bright dot in the sky and wrote down where 4 faint specks of light were sitting next to it. His name was Galileo Galilei. The bright dot was Jupiter, and on the night of January 7, 1610, he recorded those specks for the first time. He did not know what they were. He thought they might be fixed stars, but he kept looking, night after night, and the specks moved. They moved in a pattern. They swapped places. They disappeared behind the bright dot and came back out the other side. That was the moment. Not a flash of insight, just a man with a notebook, realizing that these 4 points of light were going around Jupiter, which meant not everything in the universe went around the Earth. The fourth and outermost of those specks was the biggest. Galileo himself did not name it. He numbered them. The name Ganymede came from a German astronomer, Simon Marius, who was watching the same 4 points of light at almost exactly the same time, and who suggested naming them after figures from mythology. The name did not stick for centuries. For a long time, they were simply Jupiter 1, 2, 3, and 4. Ganymede was 3. That is worth sitting with. The largest moon in the solar system spent most of the telescope era as a Roman numeral. Here is what Galileo could not know. That faint speck is 5,268 kilometers across. It is the largest moon in the solar system. It is bigger than the planet Mercury. If it orbited the Sun instead of Jupiter, we would call it a planet without hesitating. And, for the next 386 years, that was essentially all anybody knew. A big, cold, distant ball. Too far to resolve. Too dim to study. A dot in a notebook. The turning point came on October 18, 1989, when the space shuttle Atlantis carried a spacecraft called Galileo into orbit and released it. It took 6 years to reach Jupiter. It arrived in December 1995, and on June 27, 1996, it flew past Ganymede at an altitude of about 835 kilometers. Understand what that mission had already survived to get there. Galileo's main antenna, the big dish that was supposed to send data home at high speed, never fully opened. The ribs jammed. Engineers spent years trying to shake it loose from 600 million kilometers away, and eventually gave up and rewrote the spacecraft's software to squeeze the entire mission through a small backup antenna instead. The data rate dropped to a fraction of what was planned. So every measurement Galileo made at Jupiter came home through a compromised link, on a spacecraft that was already wounded before it arrived. The magnetometer team was led by Margaret Kivelson at UCLA. Their instrument did one job: measure magnetic fields. As Galileo swept past, the readings came back wrong. Ganymede had a magnetic field of its own. Not a borrowed one, not a smear of Jupiter's. Its own internal, self-generated magnetic field, produced somewhere deep inside. No other moon in the solar system does this. Not our moon, not Titan, not Europa, not one of the roughly 290 known moons out there. Only Ganymede. That was the first sign that this dot in a notebook was not dead inside. And a magnetic field means a moving, conducting interior, which raised a question nobody could answer from a flyby. What exactly is moving down there? To understand how the ocean was found, you have to understand what an aurora actually is, because the ocean was found using light, not drilling. Here is the chain. Each step is simple. Jupiter has an enormous magnetic field. It is the largest structure in the solar system that is not the sun. Charged particles get trapped in it and accelerated to high speed. Ganymede orbits inside that field. It completes one lap around Jupiter every 7.115 days, and it is tidally locked, so the same face always points inward. Those accelerated particles slam into the thin gas around Ganymede's poles. That is enough to knock electrons off atoms. Those energized atoms do not simply stay energized. They drop back down, and when they drop, they release a photon. Do that across an entire polar region, and you get a glowing belt, an aurora. Now the important part. Jupiter's magnetic field is tilted relative to its rotation axis. So as Jupiter spins, the field wobbles. And because Ganymede's auroras are anchored to the magnetic environment around it, the wobble in Jupiter's field should make Ganymede's auroral belts rock back and forth, like a boat on a swell. Calculate how far they should rock, assuming Ganymede is solid all the way through, and you get about 6 degrees. That is the prediction, 6 degrees of rocking. Now, here is the trick, and it is a beautiful one. Salt water conducts electricity. If you take a conductive fluid and wave a changing magnetic field over it, you induce electric currents inside that fluid. Those currents generate their own magnetic field, and that induced field points the opposite way. It fights the original. So if there is a large, salty, liquid ocean inside Ganymede, it would generate a counterfield. That counterfield would push against Jupiter's wobble, and the auroral belts would rock less. That is the whole experiment. You do not need to land. You do not need to drill through the crust. You just need to watch the lights and measure how far they swing. 6 degrees means no ocean. 2 degrees means ocean. And notice what this technique does not require. It does not require the ocean to be visible. It does not require a plume, or a crack, or a lucky camera angle. The ocean could be sealed under 150 kilometers of solid ice, with no opening anywhere on the surface, and this method would still find it, because magnetic fields do not care about ice. They pass straight through. That is why the same trick has been used elsewhere. Galileo's magnetometer found induced field signatures at Europa and at Callisto too, which is why both of those moons are also suspected of holding subsurface water. Induction is currently the single most powerful tool we have for finding oceans on worlds we cannot land on. You are not looking for water. You are looking for a conductor, and in the outer solar system, at these temperatures, a large conductor that is not solid metal is almost certainly salty liquid water. Now understand what you are actually attempting here. Ganymede is, on average, about 778 million kilometers from the Sun, riding along with Jupiter. Depending on where Earth and Jupiter are in their orbits, the gap between us ranges from roughly 590 million to 970 million kilometers. Radio signals travel at the speed of light. That is 300,000 kilometers per second, the hard speed limit of the universe. Even at that speed, a signal from Jupiter takes somewhere between about 33 and 53 minutes to reach us. So there is no such thing as live. Everything you have ever seen from the Jupiter system is old news by the time it arrives. If a spacecraft out there is in trouble, you find out roughly 3/4 of an hour later, and your instruction to fix it arrives 3/4 of an hour after that. There is no repair mission. There is no service call. There never has been. Then there is the radiation. Ganymede orbits about 1,070,000 kilometers from Jupiter, which puts it inside one of the most hostile radiation environments in the solar system. Electronics degrade there. Sensors get noisy. Missions have hard, calculated lifespans, defined by how much damage the chips can absorb before they stop working. Then, there is the surface itself. Ganymede's surface temperature runs somewhere between roughly -183 and -113 degrees Celsius. Water ice at that temperature does not behave like the ice in your freezer. It behaves like rock. You would not chip it with a shovel. You would need to cut it, and you would need to cut through about 150 kilometers of it before you reached anything liquid. Let that number land. 150 kilometers. That is roughly the distance you would cover in 90 minutes of highway driving, except pointed straight down, through material as hard as granite, at temperatures that would shatter most steel, in a radiation field that kills the machine doing the cutting. Nobody is drilling into Ganymede. Not in your lifetime. Probably not in the next several. And there is a further constraint that gets less attention. Power. Out at Jupiter, sunlight is about 25 times weaker than it is at Earth. A solar panel that runs comfortably in Earth orbit produces a trickle out there. Juno solved this by carrying 3 solar arrays roughly 9 meters long each, enormous wings, on a spacecraft to harvest what is left of the sun. JUICE carries about 85 square meters of solar panel for the same reason. These are not design flourishes. They are the minimum viable answer to being that far from the light. Everything about operating at Jupiter is a negotiation with subtraction. Less light, less bandwidth, less time before the radiation wins, more delay on every single instruction. So the ocean had to be proven from 600 million kilometers away by watching 2 faint belts of light and measuring how far they wobbled. That is the constraint. 2 degrees is what got through it. The observations were led by Joachim Sauer, a geophysicist at the University of Cologne in Germany. The instrument was the Space Telescope Imaging Spectrograph aboard Hubble. Hubble can see Ganymede's auroras because they glow in ultraviolet, and ultraviolet is blocked by Earth's atmosphere. From the ground, this experiment is impossible. From orbit, it is merely very hard. Sauer's team watched Ganymede's auroral belts across 7 hours of observation, covering enough of Jupiter's rotation to see the wobble play out. The belts rocked 2 degrees, not 6, 2. The result was announced on March 12, 2015. The interpretation was direct. Something inside Ganymede is conducting electricity strongly enough to fight Jupiter's magnetic field and win most of the argument. The best candidate, really the only good candidate, is a large volume of salty liquid water. I want to be precise about the title of this video because this channel does not do exaggeration. NASA and ESA did not confirm this last week. The confirming measurement is from 2015, using Hubble, and it built on hints from the Galileo spacecraft going back to the late 1990s. What has happened since is that the case has gotten stronger, not that it suddenly appeared. The headlines compress a decade of work into the word just. The science is real, the urgency is manufactured. Those are 2 different things, and the difference matters, because a discovery that took a decade of careful work is more impressive than one that supposedly happened on a Tuesday. The slow version is the true version. It is also the better story. Here is what the measurement implies about volume, and this is where it stops being an abstraction. The ocean is estimated to sit under roughly 150 kilometers of ice, and to be roughly 100 kilometers deep. Compare that to home. Earth's oceans average about 3.7 kilometers deep. The deepest point we have, the Challenger Deep in the Mariana Trench, is about 11 kilometers. Ganymede's ocean, on these estimates, is roughly 9 times deeper than the deepest hole in our own planet, and about 27 times deeper than our ocean's average. Run the volume, and Ganymede is thought to hold more liquid water than exists on the entire surface of Earth. Every ocean, every sea, every lake, every river, all of it. And this moon has more, locked under 150 kilometers of ice, on a world smaller than Mars. Try to picture the geometry, because it is nothing like Earth. There is no shore, there is no surface, there is no sky above that water, and no seabed you could stand on in any familiar sense. It is a shell of liquid, wrapped completely around a rocky interior, capped by a ceiling of ice 150 kilometers thick, with no opening, no waves, no tide in the sense you know, and no light of any kind. It has been like that, in the dark, for roughly 4.5 billion years. This is the part of the story that reframes the solar system. We grew up with a picture where Earth was the water planet and everything else was dry. That picture is wrong. Most of the liquid water in this solar system is probably not on Earth at all. It is inside icy moons, under crusts, in the dark, where nobody was looking. What remains unexplained is the detail. The 100-kilometer figure and the 150-kilometer figure are model-dependent estimates, not measurements with a tape. The salinity is inferred, not sampled. Researchers still cannot tell you the ocean's exact depth, its exact chemistry, or its exact temperature. They can tell you it conducts. That is what 2 degrees proves. Now the part that contradicted the simple model. Water is strange. Under enormous pressure, it does not just stay liquid or turn into normal ice. It forms different crystal structures, labeled Ice 1, Ice 3, Ice 5, Ice 6, and some of those high-pressure ices are denser than liquid water. That is the opposite of what you see in a glass. On Earth, ice floats. Deep inside Ganymede, ice sinks. In 2014, a team including Steve Vance at NASA's Jet Propulsion Laboratory modeled what that means for a moon this size. The result was not a single ocean sandwiched between rock and ice. It was potentially a stack. Ice, then liquid, then a denser ice, then more liquid, layered downward. A structure the team themselves compared to a club sandwich. Why does that matter? Because of the bottom. If the deepest liquid layer touches the rocky core, you get chemistry. Water contacting hot silicate rock strips minerals out of it. That is how you get the raw ingredients life needs. It is what happens at hydrothermal vents on Earth's seafloor, where entire ecosystems live in total darkness with no sunlight at all. If instead a layer of dense ice sits between the water and the rock, the ocean is sealed off from that mineral supply. Same water, very different prospects. And here is the honest answer. We do not know which it is. The models allow both. Researchers still cannot fully explain the internal structure well enough to settle it. The measurement that gave us the ocean, 2 degrees of auroral rocking, tells you a conductor is there. It does not tell you what the conductor is sitting on. That question is the reason there is a spacecraft on its way. Return to Kivelson's 1996 result, because it is still the strangest fact about this moon. Ganymede generates its own magnetic field. Roughly 290 moons are known in this solar system. Exactly one does this. A self-generated magnetic field normally requires a dynamo, a molten, electrically conductive, convecting core in motion. Earth has one. It is made of liquid iron, and it is the reason a compass works, and the reason our atmosphere has not been stripped away. For Ganymede to have one, it needs a partly liquid iron core, still churning, 4.5 billion years after it formed. On a body this small, that should have frozen solid long ago. Small worlds lose heat fast. That is basic physics. So a moon that should be cold and inert all the way through is running a dynamo in its core and holding an ocean in its mantle. 2 forms of activity on a world 5,268 kilometers across, sitting in the dark at 600 million kilometers from the sun. The leading explanation involves tidal heating, Jupiter's gravity flexing the moon and generating heat through friction, plus residual heat from formation and radioactive decay in the rock. It is plausible, it is not settled. Reproducing Ganymede's field strength in models remains difficult, and researchers are open about that. This is the pattern with Ganymede. Every measurement says the same thing. It is more alive than it has any right to be. 2 more data points, both recent, both real. On June 7, 2021, NASA's Juno spacecraft flew past Ganymede at a closest approach of about 1,038 kilometers. It was the closest anything had come to that moon in more than 20 years. Juno returned high-resolution imagery of the surface and new data on the moon's environment and radiation. Then, in July 2021, a team led by Lorenz Roth at the KTH Royal Institute of Technology in Stockholm published evidence, using 2 decades of archived Hubble data, for water vapor in Ganymede's tenuous atmosphere. The interpretation is that surface ice on the warmer daytime side sublimates directly into gas, skipping the liquid stage entirely. Be careful with that one. That vapor comes from the surface ice, not from the ocean, 150 kilometers below. It is not a plume from the deep. It is a separate finding about a separate layer, but it confirms something worth saying plainly. This moon has an active water cycle, thin and strange as it is, and it has had one the entire time we were calling it dead. There is one more line of evidence, and it is written on the outside. Ganymede's surface is split into 2 completely different kinds of terrain, and the split is obvious even in low-resolution images. About a third of it is dark, heavily cratered, saturated with impacts, and estimated to be around 4 billion years old. That is original crust. It has been sitting there, absorbing hits, since not long after the solar system formed. The other 2/3 are lighter, younger, and covered in long parallel grooves, ridges and troughs running for hundreds of kilometers, in sets, crossing and overlapping each other. Those grooves are not impact features. They are tectonic. Something stretched and cracked and resurfaced huge sections of this moon, long after it formed, and then stopped. Compare that to our own moon, which is the same basic idea, a large satellite of a much bigger body, and which is geologically dead in a way that shows. The moon's face has barely changed in 3 billion years. Ganymede's face changed, which means Ganymede had an energy source after formation, Something heated it, flexed it, and drove tectonics on a world made mostly of ice. The leading candidate is the same mechanism that may still be keeping the ocean liquid: orbital resonance. Ganymede, Europa, and Io are locked into a 1-2-4 rhythm. For every one orbit Ganymede completes, Europa completes 2, and Io completes 4. That resonance keeps their orbits slightly stretched, which means Jupiter's pull on each of them varies through every lap, which means they are constantly being kneaded. Kneading generates heat. Heat keeps water liquid. What remains unexplained is the timing. The groove terrain suggests a burst of intense activity that then largely shut off. Researchers still cannot fully explain why the resurfacing stopped, or whether the moon is in a quiet phase of a longer cycle that could restart. The surface says, "This happened." It does not say when it will happen again. So, is there anything living in there? I am going to answer that the way the researchers do, which is not the way the headlines do. There is no evidence of life on Ganymede. None. Not a hint, not a signature, not an anomaly anyone is quietly excited about. What exists is water, and water is a requirement, not a result. Here is what the ocean has going for it. It is liquid. It is large. Larger than everything on Earth's surface combined. It is stable, apparently for billions of years, which matters, because whatever happened on Earth took a long time. And it is shielded. That 150 kilometers of ice, plus Ganymede's own magnetic field, blocks the radiation that makes the surface uninhabitable. The most hostile thing about that moon is also, from the ocean's point of view, a roof. Here is what it has going against it. Cold. Dark, no sunlight has reached that water in 4.5 billion years, so photosynthesis is off the table entirely, and possibly no contact with rock, if the layered ice models are right, which would starve it of the mineral chemistry that any biology would need to get started. That last one is the crux. Europa, the smaller neighbor, is thought to have a thinner shell and a seafloor in direct contact with its ocean. That is why Europa gets more attention as a habitability target, despite Ganymede having far more water. Volume is not the same as opportunity, so the honest position is this: Ganymede has an ocean. Whether that ocean has a floor it can react with remains close to impossible to determine from here, and whether anything is in it is a question nobody can currently answer in either direction. Anyone telling you otherwise is selling something. Here is the date already locked into the calendar. On April 14, 2023, the European Space Agency launched a spacecraft called JUICE, the Jupiter Icy Moons Explorer, from Kourou in French Guiana. It is not flying straight there. It is taking a long looping route through the inner solar system, using gravity assists to build up speed, because there is no rocket that can just throw something that heavy at Jupiter directly. It arrives at Jupiter in July 2031. Then it spends about 3 years touring the system, flying past Europa, Callisto, and Ganymede, repeatedly, tightening its orbit. And then, in late 2034, JUICE is scheduled to enter orbit around Ganymede itself. That has never been done. No spacecraft has ever orbited a moon other than our own. JUICE will be the first, and it will carry ice-penetrating radar, a laser altimeter, and a magnetometer designed specifically to characterize the ocean that 2 degrees of auroral rocking implied. Radar to look for the boundary between ice and water. Altimeter to measure how much the surface flexes as Jupiter pulls on it, because a moon with a liquid layer flexes more than a moon without one. Magnetometer to measure the induced field directly, instead of inferring it from lights at the poles. The mission is expected to end around 2035, when JUICE runs out of fuel and is deliberately brought down onto Ganymede's surface, so it cannot contaminate anywhere more sensitive. Alongside it, NASA's Europa Clipper, launched October 14, 2024, reaches the Jupiter system in April 2030, focused on the neighboring moon with its own suspected ocean. So, 2030, 2031, 2034. 3 dates. If you are watching this, you will almost certainly be alive for all of them. Think about the span here. Galileo Galilei wrote those 4 dots down in January 1610. The first spacecraft touched the system in the 1970s. The magnetic field turned up in 1996. The ocean was inferred in 2015. The first orbiter arrives in 2034. That is 424 years from a dot in a notebook to a machine in orbit around it. Most of the people who contributed to that chain never saw the next step. Galileo died in 1642. Kivelson's magnetometer result came 354 years after his notebook. The team that built JUICE will be well into retirement before its most important data arrives. This is what the actual pace of discovery looks like. It is not a breakthrough every Tuesday. It is decades of instruments, slowly, in the dark, arriving late. And whatever JUICE finds in 2034, the ocean will have been there the entire time, unchanged, indifferent to all of it. The same water, under the same ice, in the same dark, since before there was anything on Earth capable of wondering about it. One moon, 5,268 kilometers across, 150 kilometers of ice, 2 degrees of light that refused to move the way it should have. That is the entire proof. Not a landing, not a drill, not a photograph of water. 2 belts of aurora, watched for 7 hours through a telescope in orbit, rocking less than they were supposed to, because an ocean underneath was pushing back. Think about what that means for everything else out there. If a moon this cold, this far from the sun, this thoroughly written off, has been holding more water than Earth for 4.5 billion years, then the question is not whether liquid water is rare. The question is how many other places we have already looked at and dismissed. There are roughly 290 known moons in this solar system. We have examined a handful of them properly. Ganymede spent 386 years as a dot in a notebook, and then one afternoon of careful measurement turned it into the largest body of liquid water anyone knows about. Nothing about the moon changed that day, only what we knew about it. That gap, between what is true and what we have gotten around to noticing, is the whole subject of this channel. In late 2034, a spacecraft will finally arrive and settle the questions the aurora could only hint at. Until then, everything we know about that ocean comes from 2 degrees. It is genuinely worth wondering what the others are hiding too. Callisto, Enceladus, Titan, Triton. Objects we have flown past once, photographed briefly, and filed away as understood. They were saying that about Ganymede in 1995. Every one of them is currently just a dot in somebody's notebook. If you want more of these, subscribe and turn on notifications, because everything on this channel is grounded in real published research rather than exaggerated headlines.